Hi students, welcome back. I'm a lecturer, Dr. Funman. So today we're moving on to the next episode on the ozone monitoring system. So as you have seen from our last class that the thickness of the ozone layer is about the total ozone content measured with some kind of specific design instrument here. And you see on the left diagram that it is called the Dobson ozone spectrophotometer. There are various parts in this spectrophotometer. As you know, the term spectral meaning you are using kinds of absorptions, excitations, right, and relaxations. And photometer means there's involvement of light. When we talk about light, we talk about electromagnetic waves. So the different parts of this Dobson ozone spectrophotometer include some kind of temperature, ammeter to measure the current flow, a battery to operate it, power pack as a backup, and a wind handle here. Okay. There are other parts that you might want to explore, but that's not important for this course. Okay. You might see that this is a very old diagram instrument. Has any improvement technology been found yet? I'm going to talk about it later. But nevertheless, what is more common in the modern world is you have this ozone sonde attached to helium balloon. And I would like to emphasize that this is not a bomb or UFO. In the next time when you see a huge balloon there, it's not like Up the movie, right? So inside there, there's a system that just detects the amount of reflections, radiations, right, using the spectrophotometry effect. Now let's proceed to the next part about Nobel Prize in Chemistry 1995. Why is that year important? Because in that year, this was jointly awarded to Paul J. Crutzen, Mario Molina, and F. Sherwood Rowlands for their work in atmospheric chemistry, particularly concerning the formation and decomposition of ozone. Now, Professor Paul Crutzen, right, he was in the Max Planck Institute for Chemistry in Mainz in Germany, in Deutschland, but he's a Dutch citizen, so he's from Holland, right? But Deutsch means Germany. Professor Mario Molina, he's from the Department of Earth, Atmospheric and Planetary Sciences and Department of Chemistry in MIT, Massachusetts. Okay. And Professor Sherwood Rowlands is from the Department of Chemistry, University of California, Irvine, California. Right, so in their work here, we talk about the ozone layer, which is the Achilles heel of the biosphere. When we talk about Achilles heel, we go back to historical Roman times, right? Why is something that's easy to be heard in the atmosphere? Because the atmosphere surrounding the Earth contains a small quantity of this ozone, right? This O3 here, right? But if the ozone is compressed to a pressure corresponding to about the Earth's surface, right? So you compress the ozone, remember the last slide? The ozone layer will only be 3 mm thick. So when you compress it, right, it's 3 mm thick like a coin, but then of course it's not compressed because it's in gaseous state due to particular theory here. It dispersed, right? It dispersed due to the low pressure there. But even though the ozone occurs in this amount of quantity, right, it is very exceptionally fundamental in our life because, right, this ozone with oxygen gas, right, they are able to absorb a lot of these UV rays, right, from the surface here. So I'm just iterating that we are being protected by this ozone here, and of course, you know, in the different parts of the stratosphere we find ozone on the ground level ozone. Some are good, some are bad. Okay. Next part. Okay, how to measure the ozone concentrations? We revisit by saying that if you compress your O3, right, and it forms a thickness of the 3 mm amount here, and if there's any part on the Earth's surface that has a compressed layer of less than 3 millimeters, is considered an ozone hole. So without this protective ozone layer, right, on the atmosphere, the animals and the plants would not exist, right, at least upon land, on ground. So therefore, if there's a very strong emphasis to understand the processes to regulate the atmospheric ozone content here. Okay. Now, I would like to emphasize about these 3 great men scientists. I'd like to pay tribute to Professor Mario Molina, who just passed away last week in October 2020 here. God bless him. They have made pioneering contributions explaining how the ozone is formed and decompose. So not only they form, remember the Chapman cycle, how they also decompose and split under the photolytic fission. And importantly, the way they have shown how sensitive the ozone layer, right, is under the influence of this anthropogenic emission of certain compounds here. For instance, if you have VOC, chlorine radicals, they break down more easily than other atmosphere. So this thinning of the ozone layer, right, has proven to be a very Achilles heel that can be seriously injured by the change in the composition of the atmosphere. And they were able to come up with chemical mechanisms, right, that affect the thickness of the ozone layer. So these few researchers really contributed to the salvation of the global environment problem that could have catastrophic consequences. Right. And next up, we'll talk about what are the agents that could cause the thinning of the ozone layer, and that will be the CFCs. But for now, let's take a pause, and I'll see you next time. Cheers.